All right, here we are on section 2.3. So we've been talking about the molecules of life, and we've even just talked a little bit about elements and atoms and things about water and pH. So now we're going to start looking at these bigger molecules that are part of organic molecules. So let's just start by how do you make and break down organic molecules? These molecules tend to be much larger, and they have lots of hydrogens and oxygens in them. And in order to link two of them together, all we have to do is a dehydration reaction. Basically, you remove a hydrogen from one molecule and a hydroxide, which is oxygen and hydrogen from another molecule, and you get two hydrogens and an oxygen, which is water. And by removing those subunits, they link them together to form the larger molecule. Since water's removed, we call it dehydration reaction. In order to break that larger molecule apart, we take a water molecule, hydrogen from one piece of it, put it onto one side of the larger molecule, and a hydroxide, the oxygen, hydrogen, add that to the other side, and you are able to break it. You're using water. Lysis means to break, so it's hydrolysis. Here's a visual of that. So you can see we've got the subunits here, and hanging off the edge of one of the subunits is an OH, and off the other side is a regular H. And you can see where water has been removed, that's dehydration reaction, and you've formed a larger organic molecule. You can do the reverse of that with hydrolysis, where you're taking the water molecule and using it to split them apart. So as we go into the rest of this chapter, we're basically going to talk about the four categories of organic molecules. That's carbohydrates, lipids, proteins, and nucleic acids. And remember, they're all organic, and that just simply means that they have CHO, carbon, hydrogen, and oxygen as their basic parts. Let's dive deeply into carbohydrates, which is the first category. So now we're in section 2.4. The monomer subunit, meaning carbohydrates, are all built out of monosaccharides, which is just a single sugar. They're made of carbon, hydrogen, and oxygen, and the ratio of hydrogen and oxygen is about 2-to-1. So there's about twice as many hydrogens as there are oxygens. The function of carbohydrates is short and long-term energy storage. In fact, glucose is a type of carbohydrate. It's a monosaccharide, and that's your blood sugar. That's where you're getting energy to do most of your work. They can be found as either simple or complex forms. So what is a simple carbohydrate? It's just a monosaccharide, and most carbohydrates come in the form, or most monosaccharides come in the form of a simple ring. You could see those carbons, hydrogens, and oxygens in the rings that we see here. And you'll notice that it's so consistent, an organic chemistry tends to not draw every carbon and hydrogen that they have. So you can see where that's been abbreviated on the right-hand side to just show that ring, but the carbons and hydrogens are there. A disaccharide is where we have linked two monosaccharides together. Again, we've used a dehydration reaction. We've taken the OH off of one side and the H off of another, removed water, and then we've linked it together and we have formed a disaccharide. This can get even larger in a polysaccharide, where you start making these larger and larger chains, and you can see those chains can be quite branched. Glycogen is the storage form of carbohydrates in animals. In fact, you have glycogen stored in your liver. So if you're ever doing a sport and you're starting to feel real tired and then you suddenly get a second wind, your liver has released some of that glycogen and given you a boost. Glycogen's made out of those simple sugars, and it gives you an energy boost. Starch is the storage form of carbohydrates in plants, and this is why you often will eat a starchy meal before you're going to go do an athletic event. It makes sure that you've got plenty of extra carbohydrates in the body. Lipids are the second category of organic molecules that we'll be talking about, these large biomolecules. Its monomer, or basic unit, are fatty acids. These molecules do not dissolve in water. You know this because lipids are fats. So if you think about taking a pan with a lot of bacon grease and trying to wash it without using a dishwashing detergent, it'll completely repel that water. Fats are a really good source of energy, and they're even found in your cell membranes. They can be found as fats, oils, phospholipids, which are the cell membrane, and steroids. So, how are fats and oils different? Well, basically just boils down to fats are an animal in origin. They tend to be a solid at room temperature, and they function for our long-term energy storage, insulation from heat loss, a cushion for our organs. So, if you have a lot of extra calories, your body will store those extra calories as fats. In plants, they tend to make oils, which are liquid at room temperature. So if you think of like your canola oil that you pour into a pan, that's a plant-based oil. Structures of fats and oils, typically there's a glycerol molecule, which you can see here, and then these fatty acids, which are these long chains of carbon. Again, fats are primarily carbon, hydrogen, oxygen, much like a carbohydrate. It's just this form is a little bit different. Carbohydrates, you saw those rings. Here you're seeing those fatty acids, which are those longer chains. We just link those together and you get these long dangly pieces off of that glycerol molecule. Be careful. You don't want to have a lot of fat in your diet. It's just so dense in calories. And they can end up causing some problems in the body. You still do need fat, though. You don't ever want to go below 5% of your diet. But if you look at this particular serving label, you'll notice that it's providing like 18% of your daily value of fat in a single cup. Maybe isn't the best choice of a food. Here's another form of a lipid. This is a phospholipid. This is what's found in your cell membrane. So you can see this picture here blown up. You're seeing those phospholipids. Again, it typically has a phosphate group up here, and then those long carbon chains dangling down that's so characteristic of lipids. A steroid is another form of lipid. It typically will have some rings. So in some ways I see the carbohydrate similarity, but you will also have those longer chains dangling off of it. Your sex hormones, cholesterol, these are all examples of your lipids. Our next category will be proteins. Thank you, guys.